Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in.
The title itself is a provocation: fast, flawless, and doomed to repeat, the false certainty of AI postmortems. It immediately challenges the idea that troubleshooting AI is somehow cleaner or more efficient than traditional software.
Indeed. The core argument is that there's a prevalent misconception, particularly in the AI domain, that failures can be quickly isolated, explained, and fixed. This often leads to a superficial analysis that masks deeper systemic issues.
So this implies a kind of intellectual shortcut where the perceived speed of identifying a problem in an AI system actually prevents a thorough understanding of why it happened.
Precisely. The speed and apparent simplicity are deceptive, creating an illusion of certainty that ultimately hinders true learning and makes recurrence almost inevitable.
To begin, what is the initial allure? Why do organizations, or even just engineers, think AI postmortems are or should be fast and flawless? What's the perceived advantage over a traditional software outage investigation?
The perception often stems from a few factors. First, the sheer volume of data involved in AI systems. There's a belief that with enough telemetry, logs, and model performance metrics, a failure can be traced directly back to a specific data point, a model weight, or a parameter setting. It feels like all the information is right there, ready to be queried.
So the availability of granular data makes it seem like a deterministic problem, almost like a puzzle where all the pieces are present, just needing assembly.
Exactly. Coupled with that is the notion of model determinism. If you feed the same input to the same model, you expect the same output. This creates a psychological bias towards thinking that if an output was wrong, the input or the model itself must have a single identifiable bug in the traditional software sense. There's an eagerness to find that specific line of code or data entry.
Which, for traditional software, often is the case. You can often point to a function, a loop, or a database query that failed. But AI systems operate differently.
They do. And the flawless part often comes from a desire to abstract away human error or systemic issues. If a problem can be attributed purely to the model or the data, it sidesteps more uncomfortable questions about development processes, deployment strategies, or organizational incentives. It's easier to blame the algorithm than the culture that built it.
That makes sense. It's a clean narrative. The model made a mistake, we fixed the model. But the paper argues this leads to false certainty. Where does that delusion of determinism truly break down in the AI context?
It breaks down in several critical areas. First, the inherent probabilistic nature of many AI models. Unlike a deterministic algorithm, an AI model isn't just following explicit instructions. It's making predictions based on statistical relationships learned from data. A wrong output isn't always a bug in the traditional sense, but potentially a low probability outcome, a misinterpretation of a novel input, or an indication that the model's confidence threshold was insufficient.
So it's not a true-false answer. It's a probability distribution. The model might have been 51% confident in one answer and 49% in another, and the 51% was still the wrong one in context.
Precisely. And this leads to the next point: emergent behavior. AI systems, especially large, complex ones, can exhibit behaviors that weren't explicitly programmed or even anticipated by their creators. These behaviors can arise from the interaction of various components, layers, or even from subtle biases in the training data that only become apparent under specific rare conditions. Trying to pinpoint a single root cause for emergent behavior is often an exercise in futility.
That's a significant departure from traditional debugging. With emergent behavior, you're not looking for a broken gear. You're trying to understand how a complex ecosystem produced an unexpected outcome. It's less about a binary fault and more about a systemic property.
Absolutely. And then there's the high-dimensional nature of the input space. Even with extensive logs, isolating the exact combination of features, context, and internal states that led to a specific failure can be incredibly difficult. It's not like a simple if X equals Y condition failing. The cause might be a subtle interplay of dozens or hundreds of variables, each contributing marginally.
So the false certainty comes from applying a traditional deterministic debugging mindset to a system that operates on fundamentally different principles. It's like trying to fix a weather system by finding the one raindrop that fell out of place.
A very apt analogy. The tools and mental models that were developed for classical software engineering don't always translate cleanly, and the belief that they do is where the false certainty takes root.
If these traditional methods are inadequate, what are the actual challenges that typically get overlooked in these fast AI postmortems? What are the missing pieces?
One of the most significant and frequently overlooked challenges is data drift and model decay. An AI model is trained on a specific snapshot of the world. The moment it's deployed, that world starts to change. New user behaviors emerge, external factors shift, or even the data collection process itself might subtly alter. The model's performance slowly degrades because its understanding of the world is no longer accurate.
So the model isn't breaking, the world around it is changing. It's like training a traffic light system in a city where suddenly everyone starts driving on the other side of the road. The system itself is fine, but its environment has fundamentally altered.
Exactly. And often, a failure isn't due to a sudden catastrophic bug, but rather a gradual accumulation of minor performance degradations that eventually cross a threshold. Detecting and attributing these to drift requires continuous monitoring of both model performance and the underlying data distributions, not just a reactive postmortem after a major incident.
What about adversarial attacks or more malicious interventions? Are those usually accounted for in a fast postmortem?
Rarely in the initial fast phase. Adversarial attacks are designed to be subtle and exploit vulnerabilities that aren't immediately obvious. A quick review of logs might show an anomalous input, but it takes deeper analysis to understand if it was an intentional perturbation designed to manipulate the model. These often require specialized expertise and tools that aren't part of a standard rapid incident response.
And beyond the purely technical, what about the human interaction with these systems? How does that complicate a postmortem?
The human element is huge and frequently underestimated. A model might be technically correct according to its metrics, but if its outputs are confusing to users, or if it reinforces existing biases in a way that harms people, then the system has still failed. These aren't typically caught by automated performance metrics alone. Understanding such failures requires qualitative analysis, user feedback, and often an ethical review.
So a model recommending a suboptimal outcome for a specific user group might not register as a technical failure in the logs, but it's absolutely a failure of the system in practice.
Precisely. And tracing those failures back to their root causes often involves examining the human choices made during data labeling, model selection, evaluation, and deployment. The fast postmortem often stops at the technical artifact, missing the socio-technical ecosystem it lives within.
This highlights a crucial point. If the fast and flawless approach focuses too much on the technical artifact, it risks overlooking the human elements that contribute to AI failures. What role do organizational culture, incentives, and data practices play?
They play an enormous, often hidden role. Consider data labeling. If annotators are under pressure to label thousands of data points quickly, or if the labeling guidelines are ambiguous, you're introducing noise and bias into the training data from the start. A model then learns from these imperfections, and its failures can often be traced back to these human-introduced issues, not just the algorithm itself.
It's like building a house on a shaky foundation because the foundation crew was incentivized for speed over precision. The problem isn't the house's architecture, but the initial build quality.
An excellent analogy. Similarly, the incentives for model deployment can be problematic. If the primary goal is to get a model into production as quickly as possible, corners might be cut in validation, testing, or monitoring setup. When a failure occurs, the root cause might be found not in the model's architecture, but in the organizational pressure to ship rapidly.
And then there's the incentive to avoid blame, which can steer a postmortem away from human factors. It's easier to say the algorithm failed than to say a team's process led to this outcome.
That's a critical dynamic. Traditional postmortems, when done well, strive for a blameless culture to uncover the actual systemic causes. But in the rush for fast AI postmortems, there's a temptation to find the most easily attributable technical cause, which conveniently sidesteps more complex human-centric issues like inadequate communication, poor tool design, or insufficient expertise.
So the doomed to repeat aspect isn't just about technical oversights, it's also about a failure to introspect on the human and organizational systems that build and operate these AI models.
Exactly. If you only patch the symptom in the model without addressing the underlying cultural or process issues that led to the flawed data or rushed deployment, then similar failures, perhaps in different forms, are almost guaranteed to resurface. The paper implies that a truly effective AI postmortem must be a socio-technical one.
Given all these challenges and the tendency for superficial analysis, what does a more robust AI postmortem actually look like? How do organizations escape this repetition trap?
It starts with acknowledging the inherent uncertainty and complexity. The goal shouldn't be to find a single, simple root cause, but to understand the contributing factors and the systemic properties that led to the failure. This requires a shift from a purely technical fix mentality to a continuous learning mindset.
So less about finding the bug and more about understanding how the system in its entirety deviated from expectations.
Precisely. This means involving a multidisciplinary team in the postmortem, not just data scientists and engineers, but also ethicists, product managers, and even domain experts who understand the real-world impact of the AI. Each perspective brings different insights into potential failure modes.
That sounds significantly slower and more resource-intensive than the FAST model.
It is, but it's an investment. It moves beyond just looking at model logs and performance metrics to examining the entire life cycle: data acquisition, labeling, feature engineering, model training, deployment, and human interaction. Questions need to be asked about the quality of annotations, the representativeness of validation datasets, the monitoring of data drift, and the clarity of human-AI handoff.
So instead of asking what broke, the question becomes what conditions allowed this unexpected outcome to occur?
That's a much more productive line of inquiry. It also emphasizes continuous monitoring and proactive analysis. Instead of waiting for a catastrophic failure, organizations should be regularly assessing model health, data quality, and the model's impact on users. This allows for detection of subtle degradations before they escalate into major incidents.
And what about the output of these robust postmortems? Is it just a list of technical fixes or something more?
It should be far more. The output ought to include not just technical remediations, but also process improvements, changes to data governance, revised ethical guidelines, and perhaps even adjustments to team structures or incentive models. It's about building institutional knowledge and resilience, not just patching a specific flaw. The goal is to evolve the entire system, human and machine, to be more robust.
So it's about building a better feedback loop, one that acknowledges the complex, adaptive nature of AI systems rather than treating them as static, deterministic software.
Exactly. It's an embrace of complexity and an admission that perfect explainability or absolute certainty in AI systems is often an illusion. The learning comes from understanding the nuances of failure, not just the surface-level symptoms.
The discussion has provided a really insightful breakdown of why AI postmortems are often insufficient. To wrap this up, what are the key insights listeners should take away from this discussion?
First, the perceived fast and flawless nature of AI postmortems is largely a myth, driven by a misapplication of traditional software debugging mindsets to inherently probabilistic and emergent systems.
Second, this false certainty leads to superficial analyses that often overlook the real systemic causes of failure, perpetuating a cycle of repeated incidents.
And third, truly effective AI postmortems demand a socio-technical approach involving diverse perspectives and an examination of the entire AI lifecycle, including human factors, organizational incentives, and continuous monitoring, rather than just technical logs.
Finally, understanding and embracing the inherent uncertainty of AI systems is crucial for moving beyond reactive fixes and towards proactive, resilient AI development and deployment.
It's about shifting the goal from finding the bug to understanding the conditions that allowed a failure to manifest, then building systems and processes that learn from those conditions.
So, for listeners, the practical implication is, when an AI system fails, the more precise question is not what went wrong, but how did the entire ecosystem of data, model, and human interaction create the conditions for this outcome?
And importantly, what lessons can be drawn to prevent not just that specific failure, but also the broader class of issues it represents, even if it means slowing down the initial response to ensure thoroughness.
That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.